But this is, I've done 2 or 3 of these, the intersection of 2 surfaces. This is kind of a good one. I picked x squared plus z squared equals 4 is a surface. X squared plus z squared equals 4 is a surface. Do you know what kind of surface that is?
Circular surface. Cylinders.
Yeah, good. Right. Your first thought is that it looks like a circle, but you're right. It's a circle in the xz plane, which, and with a missing y variable, is a cylinder. Right. Wait a minute. In the xz plane, radius 2. Yeah, you're right. It's a cylinder heading off this way. If you don't mind, that looks like the top half of it. But it is an entire cylinder. It is an entire cylinder. In both directions. So, yeah, cylinder in the xz plane. Y is missing, running out the y-axis. The other surface is y squared plus z squared equals 4. This is number 59 in 12.1. Y squared plus z squared equals 4. That's another cylinder. With x missing, I guess it's running out at me, parallel to the x-axis. It's in the yz plane, radius 2. YZ plane, radius 2. Coming out at me. Bang.
I like your shirt.
Thank you. Wow. So I'm trying to imagine that. I'm having a hard, first of all, my sketch that's trying to help me imagine it is not helping me much. You know, it's basically it's this. It's kind of 2 pipes running into each other. You know, you could say it like that. 2 pipes run into each other. They must form a curve of intersection. Curve of intersection. All right. You know what would help me is if I looked at this picture kind of in just the first octant. Now these are 2 completely full cylinders, okay? They really are, but when I draw them, my picture gets very cluttered. So I'm going to start over, and I'm going to try just kind of a first octant look at this idea. So if I'm looking in the first octant, watch this. So here's my cylinder of radius 2 in the YZ plane, and that one's coming out at me. And then, so what I'm drawing is a quarter of it, I guess you could say, sort of a quarter of it coming out at me. The other one is a cylinder in the XZ plane, radius 2. Look at, here it is, and it's running out this way. And so where do they intersect? One of them has got this curve here, and the other one's got this surface coming here. The other one's got this surface here. You know, I'll tell you what, they do have this sort of square base. This square base is an accurate picture. And I think they intersect right here. I think the curve of intersection is sort of this line. So that's a quarter of a circle there. Coming out at me. Here's a quarter of a circle there going out that way, and I think they intersect. I think there's a little crease right there where they intersect each other. And I think that crease, here's a picture of that crease in octant 1. I think that crease goes below me here. I can't draw it. I'm sorry, I can't draw it. But there's 4 more of these. There's one behind me there. There's one back behind that, underneath. I think the intersection might be some sort of diagonalized circle here. And maybe it ain't a circle at all. Maybe it's an ellipse, but there's sort of a diagonal circular intersection. That's what I've decided. And And my job is to try to help you see it and decide it, and I can tell by your faces I'm not helping you much.
Gotta help yourself first.
That's true. That's a tough one, although we revisit this problem, you know, later in chapter 14. We do double and triple integration, and we try to find volume, and this is a good problem. I like to try to find the volume of this intersection of these surfaces, the volume underneath, the volume of the solid. We're not talking about the solid right now. We're just talking about the curve of intersection where the two surfaces intersect. I think it's this crease, and I think that crease goes on around. You know, it's not a circle, by the way. Can you tell me this? Can you tell me the height of that crease right there? What's that height? 2. Can you tell me this, which you could consider a radius, I think, and underneath, I think it would have a radius of 2. But watch this. When you come out at me, because it is sitting at this diagonal, if you come out at me, that is not 2, is it? Because that's 2, and that's 2. That must be 2 square roots of 2. So we have this funny diagonalized elliptical curve. And I'm trying to draw it and show it to you. I'm having a tough time. The tough part of these problems is drawing it. What is not the tough part of this problem is when they actually say to find the curve of intersection, which is what we want. You can kind of approach it algebraically, not visually at all, really. You can sort of approach it algebraically. The curve of intersection is a vector valued function in 3 dimensions, and they suggested, and even if they didn't suggest this, I think I would suggest, I think you should come up with this thought to parameterize this. Just let x be t. That was their suggestion. But even if you didn't read their suggestion, when it's your job to parameterize something, well, just let x be t might work. If you do let x be t, it doesn't take you long to find z. What's z? If you let x be t, subtract it to the other side, solve for z. I think I get. What'd you say?
It'll be square root of 4 minus t squared.
Good. It would be plus and minus the square root of 4 minus t squared. That if I just solve for z, thank you. X was t, plug t in, solve for z, and that's what I get. Hey, if that's z, I guess I could plug that in for this z and try to find what y is. I don't think I know. If that's z and I square it, 4 minus t squared equals 4. The 4's are going to cancel. Move the t squared over. I think y is t. Or maybe I should put plus and minus t for y. So this part wasn't hard. Finding the actual equation for this curve, the curve of intersection of these two surfaces, is kind of a matter of simultaneously solving these equations. But you parameterize somebody. You let x be t. You know, there's another option, though. That's not the only answer. Let's play another game here while we're at it. You know, if you would have noticed some of the circular action going on here, it might have been smart to think about, let x be a 2 cos t. What if we let x be a 2 cos t? You know what y would be? You know what z would be?
2 sin t?
I think it would.
Bam.
It just would. You could do the math and watch it happen. Here, let's watch it happen. If we let x be 2 cos t, it would be 4 cos squared t plus z squared equals 4. If I subtract the 4 cos squared t, z squared equals 4 minus 4 cos squared t. If you factor out a 4, you get 4, 1 minus cos squared t. 1 minus cos squared is actually sine squared t. Take the square root of both sides, and z would be 2 sine t. Yeah. Awesome.
Bam. Proof.
Hey, if z is 2 sine t, now I'm going to plug that in here. If z is 2 sine t, then what's y?
Negative. Same cos.
If z is 2 sine t, then I think y, see, I mean, y is just like my x. That's how it was in that problem, kind of. I think y would be 2 cos t. You know, with these cosines and sines, I don't think I really need the plus and minus, because cosine and sine generate plus and minus values. That's kind of a trip. But I think that's a different parameterization for the same funny curve. But that was a homework question from 12.1, and they need some practice. They're tricky questions. Any other good requests anywhere?
Can we find the volume of that?
Yeah, in chapter 14. And when you say the volume, what you mean is the volume. We're finding this curve of intersection, which is funny diagonalized elliptical thing. The volume would be a solid shape there. There's a funny solid shape there. Its equator is square. It's kind of got this look. I'm sorry. It kind of looks like that on the top. There's another one of those underneath it. And the volume of that entire interior is an interesting project, yeah, for later. By the way, you can find these in the plumbing aisle of Home Depot or Lowe's. They're where 2 pieces of PVC pipe come together. This is the intersection of, you would call it a cross, where 2 pieces of PVC pipe would come together and cross each other. It would kind of look like that, except it would have these ends for you to stick your pipe in here on these ends. So we could do a field trip to Home Depot. Any other good questions? From homework, 12.1, 12.2, 12.3. 12.3's got some good projectile motion problems. We went over some of those Friday. We can always go over more, but I can always move on also. So I'll move on. So let's go to 12.4. 12.4 is very interesting conceptually, very interesting, fun to talk about conceptually. When you actually have to do some problems, it's tough, man. It's about the toughest section in this book. So, yeah, it's fun. I mean, it's cool though. So let me outline the ideas. The ideas this is in section 12.4 is this. It's called it's this new idea. It's called the unit tangent vector. He's the unit tangent vector. Unit tangent vector. He's a unit vector. Here's the formula for this guy. I'm sorry, I'm over on the back side here, but his formula is this. It's r prime of t. By the way, you can use a little common sense here. If you wanted a tangent vector to a vector valued function, you would take its derivative. You know, we've denoted his derivative velocity, but we've also noted that when we plot this derivative vector, it's tangent to the curve. So, of course, the derivative vector is tangent to the curve. But how do I make it a unit vector, you guys? Divide by his own magnitude. Divided by his own magnitude. So that's kind of common sense. The unit tangent vector is this, and it's the position curve, the derivative of the position curve divided by his own magnitude. Here's n of t. Check out n of t. N of t is known as the principal unit normal vector. Unit normal vector. And he is this. He is t prime of t. So you have to calculate t first, and then you have to do t prime of t divided by his magnitude. This is the tough one. It's kind of tough to do this. And then what you have then is this. If this is a vector valued function, it's just a curve in space, perhaps it's traveling this way, there's some orientation on it, then again, the unit tangent vector is just a derivative vector, and all derivative vectors are tangent to the curve. So he's just a derivative vector. At some point, he's tangent to the curve, but we've made him a unit vector, so we've made him 1 unit long. So if you imagine that as 1, that's 1 unit long, tangent to the curve. And the principal unit normal vector is normal to the curve. Now when I say normal to the curve, yeah, it's perpendicular to the curve, or perpendicular to this tangent vector at this point. Hey, but when I say perpendicular to the curve, look, I guess I could be this one, or I could be this one, or if I'm in space, I could be a bunch of them, perhaps. Yeah, but so that's why we use this word principal. This principal unit normal vector is the correct one, and the correct one will always point to the concave side of the curve. So it's never this one. This makes no sense. It's always to the concave side of the curve. So here's a picture of it.
How'd you figure that out?
That's what it is. The principal.
It's concave.
So I'm sort of explaining the use of the word principal. When we do these calculations, we find the principal unit normal vector. Which is, there's only one answer. But we speculated how there could be more than one answer. But when you do this math, it comes out to be the correct one. And the correct one is always to the concave side of the curve. Not sure if I get a good explanation why, but it's on the concave side of the curve. I think it's it's helping bend the curve. It's helping.
It's like centripetal acceleration.
And those are unit vectors. You know, we have our standard unit vectors. You know what they are: I, J, and K, and everything can be written in terms of I, J, and K. We write and I and J just mean horizontal and vertical. Well, forget K for a second, right? I means in the X direction, J means in the Y direction. I mean, those are nice unit vectors that are always horizontal and vertical. These are interesting, dude. These are nice unit vectors that are always tangential and normal. So they're actually, they actually kind of make their own coordinate system that's sort of a changing coordinate system. I mean, as this follows the curve, it changes. In fact, that normal vector will flip over to the other side right there. It'll be on the concave side of the curve, and the tangent vector is always changing. It's always 1 unit long. They're unit vectors, but they sort of form a coordinate system that follows the curve. You know, a good old XYZ coordinate system is stagnant. You know, it's horizontal and vertical and whatever. I mean, this is a coordinate system that's following the curve, that goes with the curve. And you can write the acceleration vector in terms of t and n. I mean, you can write the acceleration vector in terms of t and n. The acceleration vector always lives in a plane that contains t and n. I'm just going to draw an example. If this is a picture of an acceleration vector here, then at this moment, the acceleration vector is about 1, 2, looks like it's about two tangentials and maybe 1.5 normals. This acceleration vector is 1, 2, maybe a little more, 1, 2 tangentials and 1.5 normals. You're not used to this. You're used to writing an acceleration vector in terms of how much horizontal is it and how much vertical is it. And that's I and j. And you would say over 2 and up 3, you know, and that's 2i and 3j, you know. Well, I'm saying how much tangential is this? And I'm speculating that that's a 1, there's a 2, you know, maybe a 2.2. Maybe 2.2 tangentials, and then at a right angle to that would be 1 normal. That looks like 1 normal. Sorry, more like that is 1 normal. 1 normal vector, and then another, 0.6 maybe. This is total speculation, but based on this picture, I'm going to write this acceleration vector as 2.2 tangentials and 1.6 normals. That's just based on my sorry picture. I'm trying to teach you this new concept and the importance of these new things. They're these new unit vectors that sort of ride the curve. They ride the curve. And you can express the acceleration in terms of these new unit vectors instead of the old I and j. And this number that's in front of the t is called little a subscript t. And this number in front of n is called little a subscript n. And here's what they are. I'll write them over here. Little a subscript t is the tangential component of acceleration. The tangential component of acceleration. This is awesome. I mean, like I said, I love this section 12.4. I think it's awesome. I think it has power. When you start doing some problems, it gets tricky. Talking about it like this is fun. The tangential component of acceleration. It's a measurement of how much of the acceleration is tangential. And then little a subscript n is the normal component of acceleration. A formula, there's several formulas for these little guys. One formula, basic one though, is that this acceleration, this tangential component of acceleration, this language is tough, is A, the acceleration vector dot that tangent vector from above. A dot t. By the way, the dot product is a scalar, the dot product is a number, and that thing is a number. The tangential component of acceleration is some number. AN is A dot N. The normal component of acceleration. I mean, in a way, I'm done with 12.4, except I ought to do a problem. But these are the 4 big ideas in 12.4. They're big ideas. And I've tried to describe what they are with a nice little picture there. When you're traveling on a curve, you can always have a unit tangent vector. See, what have we been doing? I'm going to do this again. what we've been doing is we've been on some curve and we've been doing something. We've taken the derivative and we draw the velocity vector. And the velocity could be short or long. It could be, who knows. But there, I'm just going to say there's a velocity vector. And then we've been trying to draw an acceleration vector too at this point. We've done a lot of problems. I'll draw, here's an acceleration vector right here. And we've talked about, is this speeding up or slowing down at this moment?
Slowing down.
Slowing down, and we've said basically because, well, the A is kind of behind the velocity. It's kind of, the acceleration is kind of not helping my velocity. It's sort of hurting my velocity. It's sort of opposed to your velocity. But now I got a better way of talking. Now that I've moved into 12.4. There are two pieces of acceleration, you guys. Listen to this. You know how, in order to get velocity to change, you need acceleration. Acceleration changes velocity. But since velocity is a vector, there's two ways to change velocity. You can change its length, or magnitude, or speed, or you can change its direction. The tangential component of acceleration is the part of acceleration that's in the tangent direction. It only contributes to changing length. The normal component of acceleration is perpendicular to the direction of motion. That piece of acceleration contributes to changing direction or curve. It's like this is causing you to curve, this is causing you to speed up or slow down. I mean, this is awesome. We've taken acceleration and broken it into its two important pieces. Acceleration changes velocity, and we've got the two types of change that can happen right here. This is going to make me curve or change my direction. This is going to make me speed up or slow down. So when y'all said slowing down, part of the reason is, okay, hang on just a minute. So there's a velocity and acceleration vector. Where would be the unit tangent vector? It's tangent, and it's right here, but it's only one long. So there it is, if you allow me to call that one. There it is. Where would be the unit normal vector? It would be on the concave side of this curve, perpendicular, normal to that tangent vector. So here it is. Again, one long. So now this acceleration vector can be measured in terms of how much t is it and how much n is it. I ain't even worried about I and j anymore. I was horizontal, j was vertical. I can ask you that. How much horizontal is it? How much vertical is it? But I don't care about that. I want to know how much tangential is it? And it looks like, see if it looks like it's kind of back one tangential. Well, that's a -1 tangential. That acceleration vector is -1 tangentials, and how many normals?
1.2.
Yeah, 1.2. Is that okay with you? I'm calling this -1 tangentials and 1.2 normals. That's what I'm, just based on my little illustration. I'm making up those numbers just to put some numbers in there. So now when we look at this picture and say, oh, it's slowing down, a better real reason for saying it's slowing down is the tangential component of acceleration is negative. By the way, for years, anything to the right is positive, to the left is negative, up is positive, down is negative. But we're not thinking about left and right and up and down. We're thinking about with the direction of motion or against the direction of motion. So in this case, velocity is this way. Anything going against velocity is negative. I mean, my tangent vector is pointing this way. So one of those, two of those, three of those is positive 1, 2, and 3 of those. Behind that would be negative 1 of those, negative 2 of those. Yeah. That's good, man. This is good. And like I said, it's kind of fun to talk theoretically about these concepts. To actually do a problem is also fun, but it's work. Let's try one. I'm going to try one. I'm going to erase my little notes so I got room to work. But I'm going to give you a vector value function. I might try to find all these things. The problem is we find all these things in general at any time is what we do. Let's try it. I want to try it for this. R of t is, I'm going back to one of my most simple curves. Actually, maybe I'll change it. I'm going to change it to this curve. T squared t. That is one of my most simple curves. Do you know what it is?
Parabola.
It is a parabola, and the other day we went through the whole shebang of one of these parabolas. We plotted points. I mean, I opened chapter 12 with one of these parabolas, but it was actually a parabola. When I opened chapter 12, it was actually this kind of parabola where x was t and y was t squared. I reversed those here. I got y being t and x being t squared. I think I got probably a sideways parabola.
Yeah, y equals square root of x.
Okay, good.
Yeah.
I mean, that's right. That's what it is, I think. You can say you said it first. That's great. Yeah, I think that's what it is. It's a sideways parabola. By the way, we also talked about how you can grab a graphing calculator real quick and type it in and see what it looks like. But anyway, that's what it is. Anyway, what do I want? I want everything. What I really want is that unit tangent vector. Okay, so in order to get the unit tangent vector, I need a derivative. Derivative is easy. What's the derivative?
2t, comma 1.
2t, comma 1. You know what else I'm going to need? The magnitude of that derivative. The magnitude of that derivative. The magnitude of that derivative is a scalar quantity. It's a square root, I guess, of 4t squared plus 1. So when you take your derivative vector and divide by your magnitude, that's it. That is the unit tangent vector. The unit tangent vector is this. 2t, comma 1 divided by this magnitude. Now that really wasn't too terrible at all. We're done. We got him. We got the unit tangent vector at any time. The unit tangent vector at any moment, any time on this curve. That's his equation. All right, if I want n of t, I just erased my formulas, but n of t required me to have t prime. So now I need t prime. In order to do t prime, I need this derivative. I think I would do a quotient rule, or actually, I would like to move it up and do a product rule, to tell you the truth. So I'm going to work on t prime, but before I can actually do t prime, I'm going to call this a vector, 2t1, multiplied by 4t squared plus 1 raised to the negative 1/2. Is that okay with you? I just move that up, and now to do his derivative, I do a product rule. It's kind of funny. It's a vector times a scalar. But it's a vector times a scalar, but the product rule works. It works. So I do the derivative of this guy. 2, 0. That was awesome. And then I write down the next guy. Just write him down. Write him down. plus, write down the first guy. Write down the first guy, 2t comma 1, and multiply by the derivative of this second function here, this scalar function here. The derivative would be negative 1/2 4t squared plus 1 to the negative 3/2
times 8.
times the derivative inside, which is an 8t. Woohoo! All right, that's the derivative. We should clean them up. If you recall a little bit of Cal 1, we used to clean up this stuff with these square roots. It was a fun way to clean this up. I would always factor out this thing, and I would factor out the one that's to the lowest power. I would do this game where I would factor out the 4t squared plus 1 to the negative 3/2. Oh my goodness. All right, hold, slow down. What are we left with right here? Well, you're left with the vector 2, 0. And when you factor a 4t squared plus 1 to the negative 3/2 out of a 4t squared plus 1 to the negative 1/2, of course you're left with 4t squared plus 1 to the first. Awesome. When you factor a 4t squared plus 1 to the negative 3/2 out of 4t squared plus 1 to the negative 1/2, that's what you're left with. It's to the first. You could try multiplying it back, and when you did, you would add exponents and you would get this. Awesome. Let's keep going. What's over here? A 2t comma 1. And you factored out a 4t squared plus 1 to the negative 3/2. So that 4t squared plus 1 to the negative is out of there. You factored it out. What's left is a little negative 4t sitting there. Yeah, I should just clean that up. That's all. It'll work out pretty good in there. Inside there, if I work on cleaning that up, this gets multiplied by the 2. It also gets multiplied by the 0. So I guess I get 8t squared plus 2. If you multiply it by 2, comma 0. That'll be added to this vector, which is negative 8t squared, comma negative 4t. You guys okay? That's awesome. When you add those two vectors, you get the 8t squared plus 2 added to the negative 8, you get a 2 right there. And the 0, you get a negative 4t. This is it. This is it. This is my cleaned up derivative, I think, right? What is this? What the hell is this? T prime? Is that what this is? This is T prime. We did a product rule. We cleaned it up. Took me an hour to clean it up. But this is T prime. What am I trying to do?
I'm trying to find the principal unit.
I'm trying to get n. Right. I'm trying to get n, which is what?
That divided by the magnitude.
Oh my God, you're right. Right, I got T prime. Now I needed his magnitude. All right, don't give up yet. Hold on. I'm going to go over here where I got a little more space to work. T prime, there he is. I want to show you something. There's T prime. I'm going to factor out a 2. Is that okay? Can I pull a 2 out of that vector? So then I would have 2 out here, and then I also have this scalar out here, 4t squared plus 1 to the negative 3/2 times the vector now is 1, negative 2t. That's T prime. If you want his magnitude, you guys, maybe you should realize that the magnitude of a scalar times a vector is just pull out the scalar and do the magnitude of the vector. If you have the magnitude of 6 times v, you can pull out the 6 and just do the magnitude of v times 6. If you have the magnitude of a scalar times a vector, you can pull out the scalar. So this whole thing is a scalar that I'm going to just pull out. And then I'm going to do the magnitude of that guy. So the magnitude of that guy, square root of 1 plus 4t squared again, or 1 plus 4t squared to the 1/2.
It's under a square root.
Under a square root.
That-
Oh, okay. Yeah.
You guys okay? Yeah, under a square root, right? Or and I could put them in a square root.
It's a radicand or whatever.
What am I trying to get? N. What is n? N is t prime, which is right above this, divided by his magnitude, which is right below this. If you take t prime and divide him by his magnitude, this is beautiful. Look what happens. T prime is all this. When you divide him by his magnitude, all that cancels out. Are you following me? All that cancels out. Here's the answer. 1 negative 2t over the square root of 1 plus 4t squared, or however you wanted to say that. Keep in mind, he's supposed to be perpendicular to t. Where's t? Where's t? Where's t? Where's t? Does he look like he's perpendicular? Remember the old concept of switch when it's 2D, when it's in 2 dimensions, you can switch them and negate them. Switch them and negate one of them. Switch them and negate one of them. If you switch them and negate one of them, there it is.
Could we have just done that to begin with? And then find the magnitude?
Could we have just done that to begin with?
And then found the magnitude.
In 2D, the normal vector will be perpendicular to the tangent vector. You can just switch them and negate one. Here's the problem. You don't know who to negate. It's a 50-50 chance.
True.
Remember what I said, we want the principal unit normal vector. There's more than one, and we want the principal unit normal vector. And what I said was, when you do the math, that's the one you get. When you just switch and decide to negate one, you're not sure who to negate. You got a 50-50 chance.
So how do you test it?
I don't know.
Um,
Well, maybe by plotting some points and seeing it. It's got to be pointing to the concave side of the curve. So then I need a good picture of everything. And some in general here, I don't think I can tell. With these generalized t's, I can't tell which way it's pointing. But if I plugged in a certain t and drew a good picture, anyway, no, don't really do that. You probably should do this, although it would be quicker. This is pretty good stuff, you guys. And that, I mean, I told you it was pretty tough, but that wasn't the worst thing in the world. There's a couple more things, though. This was a vector value function I gave you, and what I'm trying to ask you for everything in 12.4, which is big T of t, the unit tangent vector in general at any time, the principal unit normal vector in general at any time, and then there was two more things. Little at and little an. The tangential component of acceleration and the normal component of acceleration. Little at, and again, I erased some of my formulas a few minutes ago, but what I said about little at is it's a dot product t. So now I think I want a. What is a? What is a? What is a? What is a? Oh, a is just r double prime? Yeah, a is just r double prime. Let me do that. R double prime. Just good old r double prime. That's a. What is r double prime? Please. R double prime, r double 2, 0. So now I want a dot product a with t. Let's do it. I'm going to do it. There it is. I can almost see it. It's this 2, 0 dot product this guy. remember when you do this dot product, you get a scalar quantity, and here it is. Little at is the tangential component of acceleration, and it'll be the x, the 2 times the 2t. The 2t is over this denominator, and then the 0 times the 1 is just a 0. So I think it'll be 4t over that denominator. That's the tangential component of acceleration at any time on this curve. I mean, we're creating these formulas in general at any time. That's what we're doing. We got n at any time. We got t at any time. Now we got little at at any time. Let's do an. An is a dot product n, which would be our a vector. Again, the 2, 0. Dot product, the n vector, which is right here. The 0 is going to cancel. I'm just going to get a good old 2 over the square root of 1 plus 4t squared. I wrote these square roots one way. I wrote, thanks to the commutative property, I can write them either way. You see those square roots? They're the same. Ta-da! 12-4 is kind of tough computations. I mean, like I said, this was the easiest problem I could think of. Sort of. I guess I could have done a line. A line would have been way too boring, though. I thought, before I'm finished finding everything I want to find, except to illustrate all this, it might be fun to draw a picture of all this at a certain time. We already speculated that this is a parabola, a sideways parabola. Let me think here. What would be a good time? Let's see what's happening at t equals -2. Let's do everything at t equals -2. First of all, where are you when t is -2? Where are you when t is -2? You're at 4, -2. 4, -2. Right, that's where you're at. All right, so that's sorry. Maybe it's more like that. 2, 3, 4, 8, 6. Right there. Hang on. Now I'm getting picky here. Hang on a second. All right, there I am. Hey, I wonder what the orientation of this curve is. That's -2. Where are you at -1? Where are you at -1? -1, -1. 1 negative, so then you're here. Okay, so you must be cruising in this way, huh, you guys? Okay, you must be cruising this way on this curve. There you are at t equals -2. At t equals -2, I wonder what the velocity is. The velocity, please. The velocity. I'd like to know the velocity.
-4.
The velocity. Oh, that's this. That's velocity. At t equals -2, you get -4, 1. Can I draw that? I would draw over 4 and up 1. And try to draw that vector. That's awesome, boy. It looks like it's tangent to the curve and everything. That's my velocity vector. So what's the tangent vector doing? The tangent vector is in that same direction, but how long is it? It's 1 long. I got a formula for it. When t is -2, I get that -4, 1, which is my velocity vector, divided, but then divided by his magnitude to make him a unit vector. So at t equals -2, my tangent vector is -4, 1 divided by his magnitude, square root of 17. So that's negative 4 over the square root of 17, 1 over the square. I can try to draw that, but it's here and it's 1 long. I'm calling that 1 long. Hey, that normal vector should be here, shouldn't it? Right, you guys? Hello?
Yeah.
Yes.
That normal vector, because it should be on the concave side of the curve. Let's just check it out. When t is negative 2, when t is negative 2, when t is negative 2, the normal vector is, remember it's kind of the same as this except switched and negated. When t is negative 2, it's 1, 4 over the square root of 17. 1, 4 over the square root of 17. That means I go over 1 over the square root of 17. That's not much. That's about 0.06 or something like that. And then up 4 over the square root of 17, which is about 0.9 something. Bless you. I go barely over and quite a bit up, and I have a normal vector there. And it's 1 long. And it's perpendicular to a curve. It's perpendicular to the curve. It's perpendicular to that tangent vector. Yeah, I'm plugging in this t equals negative 2, and things seem to be working out pretty accurately here. I'd like to see, let's see, what's the actual acceleration vector at this moment? The actual acceleration vector. Where is he? Where is he? Where is he? Where is he?
That's 2, 0.
Here he is. Yeah, he's this 2, 0. Right. So how do you draw 2, 0? Over 2 and up 0?
Mm-hmm.
Wow. Over 2 and up 0. That's kind of a trip. That's my velocity vector. Is this right?
Mm-hmm.
That's my velocity vector. And this is my acceleration vector. Over 2 and up 0. That's pretty interesting. Would you say with that acceleration and that velocity, would you say you're slowing down?
Yes.
Yeah, you're practically, it's directly opposing it almost, not exactly, but almost. You must be really slowing down. You must be slowing down because you're coming into this curve here. All right, here's what I want to know. I want to know, where are they? At t equals negative 2, these last two things. What is this tangential component of acceleration? When t is negative 2, you get negative 8 over the square root of 17. Somebody make that a decimal for me. This is my tangential component of acceleration at this moment. It's quite a bit. It's actually almost 8 over 4. It's almost 2. What is that decimal, please? Negative.
Negative 1.94.
Okay, thank you. That's little at. What's an at this moment? An at t equals negative 2, the normal component of acceleration. You plug in your negative 2 down there and you get 2 over square root of 17, which is
0.4851.
point
4851.
0.49 roughly.
Mm-hmm.
That's little an. See, when we drew this acceleration vector, here he is, he's in black right here, he's going this way. When we drew that acceleration vector, we drew him using horizontal and vertical components, which were over 2 and up 0. But if I wanted to, I can use tangential and normal components because I just figured them out. I could go negative 1.94 tangentials and about half of a normal. I'm worried my picture ain't going to look too good, but let's see what happens. There's the tangential vector. Can I do negative 1.94 of those? Let me try. Negative 1, Almost negative 2 of those. That ain't too bad. See that? Negative 1.94 of those dudes, and it's on this line. You got to go up a little bit normal in order to get to A. How much normal do you want to go? Half. Man, that ain't bad. I see that. I see negative 1.94 tangentials. That's following this line. And then up 0.5 normals to get to A. That's amazing. That's good stuff.
So this was a nice easy one, huh?
That was. That was a nice, easy one. You're right. Yeah, it's kind of, yep. So my homework in 12.4, I mean, you don't have to do 50 of these. When you look at your homework in 12.4, you ought to try a few. And so I assigned a few. Not that many, really. And there's two things going on. There's the hard work, there's the nitty-gritty hard work, and then there's the concepts. I mean, there's always two things. It's kind of always two things. And so, like I said, this is fun to talk about the concepts, and it's hard when you get down and do the work. You got to fight your way through product rules and stuff like that. But I've put this question on a test before. I wonder if you can handle this question. Watch this. This is a conceptual question. I give you this picture. I call that T. I call that N. And I tell you that A is negative 3T plus 2N, and I ask you to draw it. So that's all. That's real easy. So can you draw negative 3T plus 2N? And I mean, I've been practicing that already today, so maybe you got it. You realize that it ain't about horizontal and vertical. That's not what this is about. It's about tangential and normal, and the tangential and normal are staring right at you. So I should, at this point, I want to draw an acceleration vector. And I should go negative 3 of these tangentials, negative 3 of those dudes. I think I just did negative 3 of those dudes. And then 2 of these guys. Probably should have made those a little bigger. Maybe, hang on, let me make them a little bigger. And then 2 of these guys. And there's 1. And then here comes 2. And then that's the acceleration vector. You're right, thank you, good. It's negative 3 tangentials, and it's 2 of these normals. I mean, they form their own new coordinate system. I can draw things based on this new coordinate system of tangential and normal. Forget I and J. Don't forget it.
It's just relative.
Thank you. Yeah, 1 split second later, this all changes. You're right. This whole scene changes. This little guy, right. The tangential.
I and J is two.
I and J is nice and
it's one dimensional.
Yeah. Yeah, good. Okay. There's so 12.3 was sort of I'm backing up a second. In 12.3 there was these a lot of these projectile motion problems. So we went into that Friday. That was good stuff. And yeah, that's good stuff. Projectile motion problems. But at the end of 12.3, there's this little set of exercises, sort of 45 through 50. The word problems are tricky, but the beginning there is pretty good for you. It talks about circular motion. And it talks about circular motion like this. It says you have an R of t is, and then they just talk in general. They do this big problem in general. B cosine omega t, comma B sine omega t. So they call this circular motion. Can you tell me the radius of the circle?
B.
Thank you. The radius is B. That omega is just, I guess we could refer to it as the angular velocity if we wanted to sort of talk physics. That's what that omega is. It's the angular velocity. But here's what they ask you to do. They ask you to find the velocity in general, find the acceleration in general, find the magnitude of the velocity. What's another name for the magnitude of velocity?
Speed.
Speed. Or they also say find the magnitude of the acceleration. They want you to do all that. It's a good little bunch of exercises. I really hate to do it for you. You should do it. You want to try it now? Here, I'll shut up. You do it. How do I get velocity?
Take the derivative.
Take the derivative.
That'll be a negative b w. Yeah, negative b w sine w. Oh, sorry. B omega cosine omega t.
Yep.
All right. So Joseph is doing it. You guys with him?
Yeah. Yeah.
Yep, that was true, I agree.
And so what would you call this?
That's
Velocity.
the velocity.
Velocity at any time t, and this is all in general, right? But so what if you wanted the speed?
Magnitude.
Take the magnitude. How would you do that? The magnitude.
Square them both and times square root.
Can you see the answers? The answer's going to be nice. I don't know how far you can see into the future. If you can see into the future, you can
It's gonna be
check.
one.
Negative,
Or it's gonna be B,
it's gonna be
BW.
BW, because
because
that's the magnitude, and it's gonna be 1 sine squared plus cosine
and then you
squared.
can factor that out,
It's
and
gonna
that
be-
turns into
See, I don't have to even talk, do I? That's good. You're right. You talked yourself into it. That's what you would go do the big old square root, but the b and the omega can kind of get factored out. You can watch it happen. And watch how. I mean, you square this and you get b squared omega squared sine squared, and then you get b squared omega squared cos squared, and then how do you get? Then what?
You just factor out.
Oh, you factor out the b squared omega squared.
Sine squared plus
And you're left with sine squared plus cosine squared, which is a 1. It's still in a square root, so when we take the square root, we get
you get b omega.
b omega. Which we could just think about that as being the magnitude, right? It's there, it's sitting there multiplied by my sine and cosine. That is the magnitude, right. By the way, maybe that looks like a formula in physics. V equals R omega. Anybody ever said that? I mean, that's the speed. R is the radius. We're calling it B. But
That's singular. Yeah.
That's not.
yeah. But that's true. How would you find the acceleration?
Take the second derivative of
The second derivative. What's the second derivative?
the negative b omega cosine omega t.
Kind of.
Wait, is B?
Yeah, the
Yeah,
second.
derivative. The negative b omega cosine omega t.
So the derivative of sine is cosine.
Oh, yeah,
Omega
omega squared. My
squared.
bad.
Okay, the derivative of sine is cosine,
Mm-hmm.
and it's going to spit out another omega. The chain rule is going to spit out another omega, so you're saying negative b omega squared cosine omega t, huh?
Yeah.
And then this guy's derivative.
Negative B omega
B
squared
omega.
sine omega t.
negative b omega squared sine omega t. And that's acceleration, and if you wanted his magnitude, the magnitude of this acceleration,
What is that called?
the amount of acceleration, the length of the acceleration vector. Acceleration's a vector. It has direction and
Would it
magnitude.
be d omega squared?
And it'd be b omega squared. Yeah, it would be. This is circular motion. You know, we did elliptical motion the other day. We did a good example. We did a kind of a good example of elliptical motion. I think we did a point here where we were cruising this way. We had a velocity and maybe we had an acceleration. Remember, you know, if I had a picture like that, I might say speeding up, slowing down, and you would say, what would you say? Speeding up or slowing down, or
Speeding up,
you would say speeding up.
changing position.
By the way, it didn't look like that. It kind of went through the origin. But anyway, the angle was less than 90. It was speeding up on an ellipse. On an ellipse, your motion does speed up and slow down. I want to say on this circular motion, it's referred to as uniform circular motion. We're not ever speeding up or slowing down. We're traveling around at a constant velocity. Oh, we should have known that when we found the speed. Look at the speed. Did the speed have a variable time in it? Look, what was the speed? The speed was a constant. The speed is a constant. So the length of my velocity vector remains the same. This is good old circular motion. I don't think we did a circle once, but I don't think we got into all the details that on a circular motion, the velocity vector remains constant. It is not speeding up or slowing down. It's always the same length. And technically that's called uniform circular motion. Uniform circular motion. And the acceleration vector is always back toward the center of the circle. And I mean, it might be shorter or longer, but it's always perpendicular. Well, that's what makes you not speed up. If none of your acceleration is in your velocity's direction, if none of your acceleration is in the direction of velocity, then you're not going to speed up or slow down. It's all perpendicular. Mm-hmm. Your acceleration is totally perpendicular, so your acceleration is just causing you to turn. It's not contributing to any speed increase or decrease. Right. Right. How could you prove they're always perpendicular?
I don't know.
How could you prove that A is always perpendicular to B?
You make sure that
The dot product is zero.
The dot product is zero.
Yeah.
Yeah, hang on. You're right. Let's look at this a second. Where's my A here? Can you do that dot product with this? That first one will be a positive bunch of stuff, and the next one will be a negative bunch of stuff, and it happens to be the same stuff. Did you follow that?
Yeah.
The dot product, R double prime, dot product R prime, or A dot V
So it equals 0.
adds up to 0. Thank you. The dot product is 0. I'm asking you to see it. I'm asking you to do it. I'm not really doing it. All right. It's 12:15. I guess we'll quit today.